today we're learning about concavity and the second derivative test. Our objectives are to determine intervals on which a function is concave upward or concave downward, find any points of inflection on the graph of a function, and apply the second derivative test to find relative extrema of a function. So let's focus on some things that we understand and things we have never heard before probably. Concave upward and concave downward, we are going to define those. Concave upward means that your graph is facing upward like a smile. Back when you learned about quadratics in algebra classes, you call this opens up. So concave up is very similar to opens up, but it only has to happen on that interval. So it doesn't have to happen over the whole graph. So just from like a point A to a point B. Similarly, concave downward means that your graph opens downward. If you think about a bowl or a cup, if it is facing upward like normal, looks like this. You've got a cup with a handle on it. Over here, you've got a cup with a handle on it. Here, the cup is facing upward so it can hold liquid. Here, the cup is facing downward so it cannot hold liquid. Okay. You might notice that over here, some of the slopes of the function, even though your graph is concave upward, the function can have negative sloped tangent lines. It can have zero sloped tangent lines, and it can have positive sloped tangent lines. So you can be concave up and your graph be decreasing, concave up and your graph have a zero slope, concave up and your graph have a positive slope, and similar for a concave down graph. All right, so let's determine intervals on which a function is concave upward and concave downward. That's what that means. Next thing, find points of inflection of the graph of a function. A point of inflection is a point where you stop being concave up and you switch to being concave down, or vice versa, down switches to up. And we'll learn how to actually find those. Apply the second derivative test. The second derivative test is super similar to the first derivative test, but the second derivative test will help you find points of inflection and relative extrema. So that's an old thing. Relative extrema is mins and maxes. So let's take a look down here. F of x, that graph, has a minimum here. Of course, it's between where you have a negative slope and a positive slope. But if you only know the second derivative, we can still figure out whether that point's a minimum or a maximum. And then over here, this point is a maximum. So maybe think about, as we're talking today, where you could show that you have a relative min or a relative max. What would the concavity have to be? Concave up or concave down for each one? Okay, so definition of concavity. So let f be a differentiable function on an open interval, which means your endpoints have parentheses, right? So it's differentiable. The graph of f is what? If f prime is increasing. If f prime is increasing, the graph of f is concave up. And the graph of f is concave down when f prime is decreasing on your interval. Okay. So in that interval, the graph can be concave up or concave down, depending on whether f prime is increasing or decreasing. So what does f prime is increasing or decreasing mean? Okay. We've talked about f being increasing or decreasing. When f is increasing, f prime is positive. When f is decreasing, f prime is negative. But this takes it one step further. F prime is increasing. So the derivative of f prime would have to be positive, which would be f double prime is positive. And here, f prime is decreasing, so f double prime would be negative. The derivative of f prime would be negative. Okay, that means that concave down happens when f double prime is negative, or concave down when f prime is decreasing. So we have a couple different options to give as a reason for a graph being concave down on an interval. Now you might be looking at this and going, how do I know that f prime is increasing? Because I know that like f prime is a negative number, a positive, or 0, and then a positive number. But how do I know that f prime is increasing? Because I can see that the cup is shaped so that it's facing upward. Okay. Let's look over here with the negative slopes. Let's pick a few points in the negative slopes and just kind of estimate what their tangent slopes would be. So this would be like m equals, I don't know, like -2. And then here, m would be like -1. And then here, m would be like -0.5. Okay. Are these numbers technically getting bigger or smaller? These numbers are getting bigger. Not like an absolute value kind of a bigger. So it's not getting more steep. They're actually getting to be more shallow, but since they're negative, these numbers are increasing, right? -2 is less than -1, is less than -0.5, is less than 0, is less than 0.5, is less than 1, is less than 2. So all throughout this curve, the slopes are increasing, getting closer to being positive numbers, closer to infinity. Over here, our graph is concave down, which means that f double prime is negative. Cool. But it also means that f prime is decreasing. So let's take a look at slopes here, and we'll just kind of estimate with the same numbers. We'll say that f prime, the slope of the tangent line, is about 2 here. M equals 2. Slope of that tangent line is like 1. Slope of that tangent line is like 0.5. Okay, so these numbers, even though they are positive, they are decreasing. Okay. And then similarly over here, 0, -0.5, -1, and -2. Decreasing values for f prime. F is increasing until you get to the maximum and then decreasing after the maximum because you have positive slopes and then negative slopes. So we're going to make a chart in 3.6, and it's going to be all about like making the differences between concave up and f double prime positive and f prime increasing, and when f is positive, what is f prime, those kinds of things. That one didn't make any sense, but we'll make a chart so that you don't have to go back through your notes and try and make sense of it all again. We'll organize it. All right, test for concavity. So how do you know? Let f be a function whose second derivative exists on an open interval I. So you can take two derivatives. This is also called twice differentiable. If f double prime is positive for all x values in your interval, then your graph is concave up in that interval. Okay. So I is just a fancy way of saying like from A to B. So we've seen this one a whole bunch, from A to B. Okay. So if f double prime is positive, then f is concave up, and if f double prime is negative, f is concave down. You might just write that out so it's like slightly different wording for yourself. Okay. Determine the open intervals on which the graph of f of x equals this polynomial is concave upward or downward. So what do we need to show? We need to show that f is a function whose second derivative exists on an open interval. Well, we need to show that f of x is twice differentiable. We know that f of x is continuous and differentiable because it's a polynomial. Polynomial means twice differentiable. Okay. So let's find our derivatives. What is f of x equals x to the 4th power minus 4x cubed plus 2. First derivative is 4x cubed minus 12x squared plus 0. The derivative of this, f double prime of x equals 12x squared minus 24x. Okay. Concave upward or downward. We know that our graph is concave upward when f double prime is positive and concave downward when f double prime is negative. So just like when we did the first derivative test, let's set f double prime of x equal to 0. And as I do that, I'm going to go ahead and factor this. 12x times x minus 2. Okay, let's set each factor equal to 0. 12x equals 0, or x minus 2 equals 0. So divide by 12 and add 2. These guys right here are called possible points of inflection. And I've got points of inflection just down below. Points of inflection. They are possible points of inflection. That is really similar to when we did the first derivative test, when we found all of where the first derivative equaled 0. These guys would have been critical numbers in the first derivative test, and they would have been possible mins and maxes. Okay. Here they are possible points of inflection. They might be points of inflection, they might not be. So we have to say possible until we prove whether or not they actually are. Okay, next thing we are going to do is we are going to set these two numbers up on a second derivative test. That's one of those number lines. Okay, so let's write out 0 and 2 on our number line. 0 and 2. And we know that f double prime of x is 0 at both of those spots. Our x to the fourth graph, that is continuous everywhere for all x's. So I'm going to put arrows on the ends. There's no end points that we have to deal with. Okay, so we just need to pick numbers that are between 0 and 2 and are bigger than 2 and less than 0. So how about, let's do -1, 1, and 3. Sounds good. Now your goal is to find what is f double prime of -1. And we just care about whether it is negative or positive. I'm going to show you how to plug that into the factored version of f double prime instead of into the original function, but you can just plug it into the original function, okay? The original f double prime function. So you can plug in -1 here and here, or you can plug it in here and here. And this is the one we're going to test out today. So f double prime of -1 equals 12 times -1 times -1 minus 2. 12 times -1 is -12, and -1 minus 2 is -3. When you multiply together a negative number times a negative number, you get a positive number. So once you turn this into factors, all you care about those factors are whether they are positive or negative. It saves you from having to add and subtract with kind of big numbers to figure out positives and negatives. You're multiplying together factors that are positive and negative. So positive times negative is positive, or multiply those together to get a negative, and then negative times negative is positive. We'll do this again for some practice. So we know that f double prime of -1 is positive. Let's test it out with 1. F double prime of 1 is 12 times 1 minus 2. So this is 12 times 1 is 12, and 1 minus 2 is -1. 12 times -1 is a negative number. We know it's -12 because that's fairly small numbers, but we don't care. We just care that it's negative. So boom, negative number. And then let's do f double prime of 3. And of course, you'll get the exact same number, not just the exact same sign, by plugging it into the factored version. So we got 12 times 3 minus 2. 12 times 3 times 3 minus 2 is 1. Positive times positive times positive is positive. Okay, what I did here was positive times negative is negative. What I did here was negative times negative is positive. All right. So f double prime of 3 positive. We've got this. Now we need to show whether our graph of f of x is concave up or concave down on certain intervals. So here's how I write those sentences. I write them ahead of time. Okay. What I would write is, you can write this just on whatever blank space there, but I'm going to grab another sheet of paper just for room. So on the interval from negative infinity to 0 and from 2 to infinity, f of x, or just f, it doesn't matter, is concave up because f double prime of x is positive. Okay, so you have to say the where, like at what x values. You have to say what the thing is that's happening, what do you care about, and then why. How mathematically do you know? What's your reason? Okay. And how I actually write those sentences is I start with on, and then I leave a blank, and I say f of x is concave down because f double prime of x is, well, how do we know f of x is concave down? Well, when f double prime is negative. And then I look back at my work, and my work says that f double prime is negative between 0 and 2. There it is. You are done with your reasoning on there. So let's talk about points of inflection. Points of inflection occur when our graph switches concavity. If the graph of f switches concavity. Switches concavity, changes concavity. There's another way to say that f double prime of x changes signs. This is a really big deal. That's going to be your reasoning. So if you are told that your graph switches concavity, great. But if you know by mathematics, by figuring out that the positive and negative signs are switching, right? We switch from positive to negative here. We switch from negative to positive here. Then you can show that f has a point of inflection at x equals 0 and x equals 2. So those possible points of inflection, x equals 0 and x equals 2, yes, they are points of inflection because f double prime of x changes signs at those x values. Don't say changes from positive to negative or negative to positive. Go with the generic version because it works for both. All right. Let's switch over to the second page of this, points of inflection. Okay, if c, f of c, so that's the x value, y value, right, is a point of inflection on the graph of f, then either f double prime of c equals 0 or f double prime does not exist at x equals c. Okay, so this point on f of x has to exist, okay? You're not allowed to have like f of x have a hole in your graph or a vertical asymptote in your graph. That point has to exist. It is a point of inflection. Okay, then either f double prime of c equals 0 or f double prime does not exist. So you can have your second derivative undefined. So f double prime is undefined, which usually means that value c makes your denominator 0. I'm going to say denominator equals 0 when x equals c. Usually the denominator of a fraction would equal 0 when x equals c. Okay, you'd have like a hole in your graph when that happens, or a vertical asymptote when that happens. So f double prime does not exist there. F double prime of c equals 0. That came across back on the previous page. I'm going to bring that back. F double prime of x equals 0 here and here. This just happened to be a polynomial, so the second derivative was kind of beautiful. But when we have something that has small fraction exponents and you take a second derivative, we'll end up with fractions. If you have negative exponents to begin with, you'll have some negative exponents to get to fractions, those kinds of things. All right, let's go ahead and just find the points of inflection, and then we'll come back to this. So determine the points of inflection and discuss the concavity of the graph of f of x equals x to the 2/3 times x minus 5. I'm going to rewrite that function here so I can zoom in on it. X to the 2/3 means the cube root of x squared. So if x was like 8, you would take the cube root and get 2, and then you would square it and get 4. Okay, looks like that, or that. Okay. We can take the derivative of this exactly how it is by using a product rule. However, we can distribute the x to the 2/3 to x to the first minus 5, and we're going to do that so we don't have to do quite as much product rule derivative stuff. So f of x equals x to the, let's see, 2/3 plus 1 is 5/3 minus 5x to the 2/3. Let's take two derivatives because this is the second derivative test. Points of inflection, you need second derivative. F double prime of x, nope, gotta take one at a time, Miss Campbell. Slow your roll. All right, f prime of x equals 5/3 x to the 2/3, right? 5/3 minus 3/3 is 2/3, minus 2/3 times 5 is 10/3 x to the 2/3 minus 1/3, minus 1 is negative 1/3. We do not want to switch this to a fraction yet. We don't want to put that in the denominator because we still have to take another derivative. F double prime of x equals, multiply 2/3 times 5/3. You're multiplying top times top, bottom times bottom. I'll go ahead and show it out. 2/3 times 5/3. X to the 2/3 minus 1 is negative 1/3. Plus negative 1/3 times negative 10/3. X to the negative, and then negative 1/3 minus 3/3 is negative 4/3. Okay. Multiply those fractions, top times top and bottom times bottom. And as we do so, I will move any x with a negative exponent down to a denominator. So it's f double prime of x equals 10/9 times, I'll write it with a root, the cube root of x, plus, because negative times negative, 10/9. Hey, look, those numbers match. Interesting. Times the cube root of x to the 4th. Okay. We want to see, where does f double prime of c equal 0? And where does f double prime not exist? So where can we make the denominators equal 0? That's the big deal. Where do denominators equal 0? Or where does like f double prime of x's domain not work out? If you plug in 0 for x, 0's cube root is 0 times 9 is 0. 10 divided by 0 does not work. Over here, same deal. If you plug in 0 here, your denominator is 0. That's bad. So f double prime of 0 is undefined. So when we draw our number line, 0 is going to be undefined. Okay, let's now set this guy equal to 0. This is not the prettiest thing to solve, but we can still do it. 0 equals 10 over 9 times the cube root of x plus 10 over 9 times the cube root of x to the 4th. The easiest way to solve this is going to be to move one of those fractions over to the left. It doesn't particularly matter which one of the fractions moves left. Let's move the first one. So it's going to be negative 10 over 9 times the cube root of x equals positive 10 over 9. There we go. 10 over 9 times the cube root of x to the 4th. Okay, now let's say that we want to get x by itself. What we can do is we can multiply both sides of our equation times 9 times the cube root of let's just multiply both sides by 9 over 10. What that's going to do is the 9s are going to cancel, the 10s are going to cancel, 9s cancel, 10s cancel. So we'd still have that negative there, but then it's 1 over instead of anything else. Okay, and it's thinking about it now, it's going to be easier to do this as exponents instead of roots. So I'm going to switch them back to the 4 over 3 and the 1 over 3 when I do my rewrite here in a second. So 1 over x to the 4/3, there's our equals, and negative 1 over x to the 1/3. Gonna do that rewrite. Negative 1 over x to the 1/3 equals 1 over x to the 4/3. Okay. There's choices on what to do next when solving. What I'm going to do is multiply times x to the 4/3 on both sides. I picked that one because it was bigger than 1/3. 4/3 bigger than 1/3. So this is negative x to the 4/3 over x to the 1/3 equals, hey, those cancel, so we're left with 1. And then let's use some algebra 1 exponent rules. Negative x to the 4/3 over x to the 1/3. If you have the same base, you can subtract your exponents because it's division, right? 4/3 and 1/3 subtracts out to be 3/3. 3/3 is 1, so that's just x. 4/3 minus 1/3 is 3/3, which is 1. X to the first is the same thing as x. Dividing both sides by -1 is x equals -1. Woo! So this guy is a possible point of inflection. POI. Possible point of inflection. Let's go ahead and put x equals -1 and that 0 on a number line up above. -1 gave us f double prime of x equals 0. All right. We know there's arrows on both sides because our original function didn't have any holes or asymptotes or anything like that. We are going to plug in, let's pick -2, -0.5, and 1. Just like -1 is a possible point of inflection, 0 is also a possible point of inflection because 0 is defined on f of x, even though 0 is not defined on f double prime. Okay, 0 makes this work out. It's just 0. F of 0 is 0.